everyone. I hope all of you are doing well. Yeah, so we will today I welcome you all to the week 4 live session of the NPTEL course NMR Spectroscopy for Chemists and Biologists. So we will wait for 2-3 minutes and then we can start the course. So I will wait for people to join, other learners to join, and then I will start with today's lecture. So I hope all of you have gone through the week 4 lecture. In the week 4 lecture, the concepts that were discussed were related to the different errors in that arises due to RF pulse, and then we had also seen some concepts that were related to Fourier induction, FID, right? Free induction decay. And mainly we had in the later part of the lectures, we had also gone through spin echo pulse sequence and how it can be used for detecting NMR in Fourier transform NMR. So it was a continuation of the practical aspects of Fourier transform NMR, and also we had dealt with spin echo, the spin echo pulse sequence. So what I will do today is I will discuss a few some of the important concepts that will help you in solving your week 4 assignment. And other than that, I will also discuss some questions that were asked in week 3 assignment, and I will discuss them. And also, if you have any doubt in the previous week questions, I can take up those questions. So I will start sharing the screen. Just a second. I hope the slides are visible. Yeah, so good evening, everyone. I am Akash Jyoti Pathak, and I am a PMRF TA for the course NMR Spectroscopy, NPTEL course NMR Spectroscopy for Chemists and Biologists. I'm a PhD scholar in the Department of Biosciences and Bioengineering in IIT Bombay, and currently I am in the second year of my PhD, and I am in working in an NMR biomolecular NMR spectroscopy lab. So yeah, today we are discussing about the week 4. We are currently we will be dealing with the week 4 the lecture, NPTEL lectures, and we will understand a few concepts that were discussed in the week 4 lectures. Yeah. So So let's start with the with today's lecture. Yeah. So in the last session, we had discussed about Fourier. We had discussed about free induction decay. So what is free induction decay? We understood that when an RF pulse is applied. So yeah, when an RF pulse is applied, it causes the bulk magnetization to flip from the z-axis. Z-axis, the bulk magnetized in its equilibrium position. The bulk magnetization is oriented in the along the z-axis, and when an RF pulse is applied, it causes the bulk magnetization, or it causes the magnetization to flip from the z-axis to the xy plane. Now, depending on the direction in which the RF pulse is applied, so whether it is applied in the x direction along the x-axis, or along the negative x-axis, or y-axis, negative y-axis, it causes and also the it also depends on on the axis, and also what is the pulse. So is whether it is a 90-degree pulse or whether it is a 180-degree pulse. So a 90-degree pulse means that when we apply a 90-degree pulse along the, so for example, we are applying a 90-degree pulse along the x-axis, it will cause the magnetization to shift from the z-axis to the negative y-axis, right? And how do we get the direction along which this the bulk magnetization will fit? We had seen that we will apply the right hand thumb rule. So using the right hand thumb rule, we can determine the direction in which the bulk magnetization will flip from its equilibrium z-axis to the xy plane. Okay. So yeah. As you can see in this figure. So just a second. So as you can see in this figure, that in this figure, the RF pulse is applied positive along the positive x-axis, and this RF pulse has caused the bulk magnetization to shift from the z-axis to the negative y-axis. Now, now we also learned that the RF pulse is applied in a short burst. It is applied in the scale of microseconds. So for few microseconds, this RF pulse is applied, and then once this RF pulse is removed, the magnetization, this bulk magnetization, yeah, yeah. So just a second. Yeah, yeah. So what we were discussing is when the RF pulse is applied, and depending on the direction in which the RF pulse is applied, whether it is applied along the positive x-axis or the negative x-axis, and also whether it is a 90-degree pulse or 180-degree pulse, it will accordingly cause the magnetization to shift from its equilibrium z-axis to the xy plane. Okay, so as you can see in this figure, what they have shown that the RF pulse is applied along the x-axis, along the positive x-axis, and this has caused the bulk magnetization to shift from the z-axis to the negative y-axis. Now, once this RF pulse is removed, this magnetization will start to decay. So it will start to decay, or means that it will start to dephase out from the transverse plane. The transverse plane is the xy plane, and it will start. It will start to decay, and it will follow a spiral path, and this magnetization it moves from the xy plane, and it will shift back to its equilibrium position along the z axis. So when this magnetization when this magnetization starts decaying, there is because of the fluctuating magnetic field components along the x-axis and along the y-axis, there are a signal is detected. This due to the fluctuating magnetic fields by the different precessing nuclear spins, we detect a signal in the along the x-axis and y-axis. Okay. And so this if Fourier induction decay, this has both x component and y component. And the x component, so this equation, what it shows that the x component is related to the time as in the cosine. It is in the cosine, and along the y-axis it is related in the sine function. And this g of t G of t, this is the Fourier transform of all the frequencies. This is the Fourier transform of all the frequencies in the which are decaying. Okay. So FID, so what is Fourier induction? The free induction decay. The free induction decay is the response of the spin system to an RF pulse. The RF pulse rotates the equilibrium Z magnetization into the XY plane. So for a 90-degree pulse, this magnetization then precesses and decays as the system returns to equilibrium. And as the system will decay and return to equilibrium, the signal is detected by the receiver due to the fluctuating magnetic fields of the nuclear spins. Okay, the precessing magnetization induces a signal in the receiver kept in the XY plane. Now what happens is this Fourier in this free induction decay, this has both an X component and the Y component. Now we can detect this Y component is related to the time as a cosine function. And we can either detect the Y component or we can detect the X component. So if we detect the Y component, then we can in the time domain, we get a signal. As you can see that the cosine function is this starts from 1 and moves to 0, and then this is the profile of in the time domain. Now if we do the Fourier transform of this time domain, this in this after Fourier transform in the frequency domain, the Fourier transform basically helps to convert the time domain into the frequency domain. Okay, now in the frequency domain, what we see that this cosine function, if the receiver is placed in such a way that it detects only the Y component, then the Fourier transform of this Y component gives us an absorptive line shape. So absorptive line shape, this we had also discussed in the initial few weeks, that this has a symmetric, it is a symmetric line shape, and but and now if we if the X component is detected, this X component is related to the time as in a sine function. So this X component, Fourier transform of this X component gives a dispersive line shape. Okay, so depending upon whether the X component or the Y component of the magnetization is detected following a 90X pulse, the FID has a sine or cosine functional form for a single frequency. Okay, so we can either, I hope this is clear. So what we were discussing is that the free induction decay, because of the fluctuating magnetic fields, this has both an X component and a Y component. The X component is called the real component and the Y component is called the imaginary component. Now we can either detect the X component. So if we detect the only the X component, then the Fourier transform of this gives us a dispersive line shape. And if we detect the Y component, this Y component in the time domain, this will have a this will have a it follows a cosine function, and on Fourier transform of this cosine function we get an absorptive line shape. Now what is quadrature detection? Quadrature detection is it detects both the X component and Y component simultaneously. So as you can see this figure in the bottom of the slide, you can see that in quadrature detection, what is done, this X component. So in the red line, as you can see, this is the sign, this means this is the X component, right? This is the X component, and in the black profile, this is the Y component. So in quadrature detection, both this X component and yeah,
Can you go back to the last slide?
yeah,
Yeah. Can you explain to me how MX and MY, so they are the magnetization from the X and the Y axis, right?
yeah.
So why is X on the magnetization from the X axis is showing a dispersive line shape?
This is showing a okay. Why this is showing a dispersive line shape? Okay, so for this there are certain relations, mathematical
The
relations.
sine wave itself, right? From the sine wave, we are getting these sorts of 0 and 90 degrees.
Mm-hmm. 0 and 90 degree. Yeah, right.
Okay. Okay. Okay.
Hmm.
Continue.
Uh, Yeah, so there are a few so this has a long calculation. So why do we get this dispersive line shape? After there is an equation, you solve this, and then this produces a dispersive line shape. Okay, you can go back to the lecture and watch this one. This is explained in greater amount of detail. So what this quadrature detection does is that this x and y a component are detected simultaneously. We can say that the real component and the basically this is the real component. This absorptive line shape. This is what we detect in an NMR spectra, right? This dispersive line shape. This is called the imaginary component. This is not detected, but this is required for phase corrections. Okay, so. So combination of these two, simultaneous combination of these two components, and on Fourier transform of this frequency domain to the of this time domain to the frequency domain gives us a absorptive line shape. So the quadrature detection is used in NMR to capture both the real and imaginary component of the FID signal. What was the real component? The this cosine component is called the real component. This and the sine component is called the imaginary component. Okay, this allows for full reconstruction of the frequency domain spectrum since the methods need to separately detect the real and imaginary components. Two detectors are required. So how does this quadrature detector simultaneously detect both the x and y component? So there are two detectors, and these two detectors are orthogonal to each other, and so it can detect both the x component and y component simultaneously, and then this is combined and processed further to further data processing. This gives us the this is what we see in an in the NMR spectra, or when we are recording the data we can see this one. Okay, carrier frequency, these two detectors work together to capture the full signal. And in a quadrature detector, good quadrature detection, what is done? The carrier frequency is placed in the middle of the spectrum to ensure that the full spectrum is detected symmetrically. Uh, so, this one this about regarding this last concept, I will explain this in the next slide about why it is placed in the middle. So. Yeah. So after the understanding this concept, I would want you to solve this question that in a free induction decay, the first data point has zero intensity. Fourier transform of this FID leads to. So there is a hint also given in this slide, in the bottom of this slide. So here what they have for the question, this question was asked in week 3 assignment. So free induction decay, the first data point has zero intensity. So this is the free induction decay. Just a second. Yeah. So this is the free induction decay, and as you can see, the first point of this free induction decay has zero intensity, right? Has zero intensity. Now, if we are so basically, what it is trying to say is that it has zero intensity means it is detecting only the x component, because in the x component we as we had seen that this x component is related to the time related to the time in as sine function So if the first data point has zero intensity, this means that Fourier transform of this will give us the dispersive line shape. Okay. So that is the answer. So for Fourier induction decay, the first data point has zero intensity, and the Fourier transformation of this FID will give us a dispersive line shape. Okay. So this was a simple question that was asked. Now the another question that was this was this you can also try this question after you have since we have just discussed the concept. So in a quadrature detection, the carrier is placed at dash and requires dash detectors. So that we had discussed that the carrier is placed at the middle of the spectrum. So why it is placed at the middle of the just a second. Hmm. Yeah, so why the carrier frequency? What is the carrier frequency? So carrier frequency is the frequency of the RF pulse, basically. It is the frequency of the RF pulse, and we set the, so depending on what type of signal we want to detect, we have to set the carrier frequency. So whether we are what type of nuclei we want to excite, and all these factors will control what will be the frequency of the RF pulse. And this frequency of RF pulse is called the carrier frequency. The carrier frequency is placed at the center of the spectrum to detect both the plus omega I and minus omega I frequencies. Okay, so if you see this, so this one, as we were discussing this cosine component, this cosine for Fourier transform of this cosine component will give us two frequency, minus omega I and plus omega I. So Fourier transform always gives us this these two components. These two frequencies, it produces a mirror image across this or yeah, mirror image or uh, across this zero line. Okay, so so that this one is initially in a NMR spectrometer. This one is done to see if the plus omega I minus omega I, if they are equal or not. So this is, yeah, usually placed in the center of the spectra that we want to measure. And why two detectors are required? So detectors are required to capture the real component and imaginary component, or the X component and Y component simultaneously. That is why two detectors are required in a quadrature detection. Okay. Now, coming to dwell time. So, what is there? This is another concept. The based on which few questions are asked in assignment 4 and assignment 3. So, dwell time. What is dwell time? So, basically, when we are recording the spectra, the dwell time is the it is the, yeah, dwell time is the time interval, or it is the time between two data points, or between 2 points. What is the time is called? It is called the dwell time. So the time interval between consecutive points in the FID is constant and is called the dwell time. So when we are recording the data, the this this is continuous. This Fourier induction decay, this is continuous, but the spectra is recorded in discrete units, right, at particular points. Okay, so time interval between two data points, between 2 points is called the dwell time. And dwell time is determined by the sampling theorem. We will understand what is sampling theorem in the next slide. So the Fourier induction decay contains all frequencies in the spectrum. So each data point has contributions from all these frequencies. The dual time basically it controls what will be the resolution of our NMR spectra. So it is important to understand this concept. And this dwell time is chosen to match the largest frequency in the spectrum, ensuring all lower frequencies are accurately represented. Okay, so both the lowest intensity and the highest intensity signal should be detected, and that is why the dwell time must match the largest frequency in the spectrum. So this is the dwell time, the time between. Just a second. Now, what is the acquisition time and resolution? So acquisition time is the time for which we are collecting the data. Okay, so what we discussed, that tau is the, so tau is the time interval. What is the time interval between two data points? Okay, and now the acquisition time is the time for which we are recording the data. For which we are recording the data. So for example, this is the this is the TAQ. So what will be T acquisition time? So acquisition time will be equal to the number of data points we collect and what is the time interval between each data point. Each data point, what is the time interval between each data point? That is given by dwell time. And if we multiply this dwell time by the number of data points that we record, that is n. N is the number of data points that we record. And if we multiply this, then we get T acquisition, which will give us the total time for which the data is recorded. Okay. So n is the number of data points collected and t tau is the dwell time. Now dwell time is equal to 1 by 2 times spectral width. So this concept was discussed. This dwell time is inversely proportional to spectral width. And what is spectral width? Spectral width is the maximum frequency that is represented in the spectra. Spectral width is actually the maximum frequency that is represented in the spectra. So the spectral width is the range of frequencies that can be observed in the spectra, and so it will be the range of frequency, but the spectral width is taken to be the value of the spectral width will be the maximum frequency that is present in this range of frequency. Okay, so according to so what is the sampling theorem? So sampling theorem is also called as this is the same as Nyquist theorem. So Nyquist theorem, what does it say? It says that to accurately sample a signal without aliasing. So what is aliasing? Well, aliasing we will understand in the next slide. That aliasing is signal folding, is also known as aliasing. The sampling rate must be at least twice the maximum frequency present in the signal. So the maximum frequency that is present in the signal, the that twice of that will give us the sampling rate. Okay. So the largest frequency represented by the dwell time is omega max, and that is equal to 1 by 2 tau. So T acquisition gives us n by 2 omega max. So basically what is T? What here it is saying is acquisition time is equal to number of data points into the time interval between two data points. And this tau is related to omega max as 1 by tau is given as 2 omega max. So T acquisition is n by 2 omega max. Okay, is it clear? Is this point clear? Okay, so based on this concept, you try to solve this question. So in this question, so if you solve this question, you will understand the concept better. So in an FT-NMR experiment, the spectral width is set to 5000 hertz. And 1024 data points are collected. Calculate the dwell time for this experiment. Okay, so spectral width is omega max. So maximum frequency that is present in the spectra. Spectral width is same as omega max, and that is equal to 5000 hertz. And you have to calculate so 1024 data points are collected, and based on this information, you have to calculate the dwell time, the total acquisition time, and the third question is whether if you want to record a signal which is of 6000 hertz, will there be any aliasing or signal folding? So just now we discussed what is dwell time tau. Tau is 1 by 2 times the spectral width. Okay, tau is 1 by 2 times spectral width. So you apply this formula and you tell me answer of this first part. And for the second part, you can apply this formula. T acquisition is equal to n into tau. I can apply n into 1 by 2 times the spectral width. And for this third part, you have to apply the concept of Nyquist theorem. Okay. So try to solve this question. I'm giving you 2 to 3 minutes. You can apply the formula directly 1 into 2 times the spectral width. The spectral width is 5000 hertz. Right. And so this will be 1 by 10,000. So how much will be this answer? So hertz means per second, right? So this will be 0.1 into 10 to the power minus 3, which means 0.1 millisecond. 0.1 millisecond is the dwell time for this experiment. Means there are 1024 data points and each data point have been recorded. So between two data at a time interval of 0.1 millisecond. Okay. Recording the data points at intervals of 0.1 millisecond. So that is the dwell time for this experiment. And the total acquisition time. So you know the number of data points. So number of data points if you know, and what is the time interval between two data points? It is 0.1 millisecond, right? It is 0.1 millisecond. If you calculate this, you will get the total acquisition time. 0.4 millisecond you can, or you can convert this into second and you can get 0.1024 seconds. Okay. Now if this signal contains a frequency component of 6000 hertz, will aliasing occur? Explain why or why not. So you have to calculate the Nyquist frequency to understand if there will be aliasing. Okay. So how will you calculate the Nyquist frequency? So Nyquist frequency will end at Nyquist frequency should be 2 times the sampling rate. 2 times the sampling rate. Okay. So, so, so what you can, so as you had seen here also, the sampling rate in this question is what? Sampling rate for this question is 2 times the spectral width. It is 10,000 hertz. Okay. So this 6,000 hertz. So I have to see if this 6,000 hertz. So this Nyquist frequency, then what would be the Nyquist frequency in this case? Since Nyquist frequency is 2 times the sampling rate, the Nyquist frequency would be, this would be 10,000 by 2, 5,000 hertz. Okay. So this 6,000 hertz, this 6,000 hertz lies beyond this 5,000 hertz. So there will be aliasing. Okay. So you can look at the solution. Yeah, so dwell time is 1 by 2 times the spectral width. So the dwell time is dwell time is 100 microsecond, right? So I reported in the millisecond. So in microsecond, this would be 100 microseconds. And the acquisition time is number of data points into the dwell time. So 102400 microseconds is the acquisition time. And to understand whether aliasing will occur or not, we will calculate the Nyquist frequency. The maximum sampling rate is 10,000 hertz. So the Nyquist frequency would be 5,000 hertz. And so the aliasing will occur because this 6,000 hertz is lying beyond this 5,000 hertz. Okay. Yeah. So what is aliasing or what is folding of signal? We will understand this concept. So the folding of signal is necessary. So before collecting the data, before collecting the NMRs, and recording the NMR spectra, or before collecting the data, it is necessary to know the frequency range. The depending on our protein of interest or depending on which amino acid side chain or which residues we are trying to probe, we must know the frequency range. So if the spectral range and the offset frequency is not appropriately selected, the signals present outside the spectral region fold into the selected region with a distorted phase. So as you can see in this figure, this is the so for example, this is the spectral width from here to here. So this is the spectral width. So if the spectral width is not properly is not appropriately selected, then what will happen? The signals which are present outside the spectral region. So this is our spectral region. This is our spectral region, and the signals which are present outside the spectral region, they folds back. They fold back into the selected region with a distorted phase. So as you can see, there is a signal which is present outside the spectral width, and because this signal was not the spectral width was not appropriately selected, this causes the signal which is present outside the spectral width to fold back into the spectral width with a distorted phase. Okay, so the central spectrum of f omega n equal to 0 gets into it omega dash from the spectrum on its left. So for example, so follow this figure. For example, there is an omega dash frequency on the left of the spectral width. And since the spectral width is not appropriately selected, what happens is that it causes the omega dash frequency from the left side of the spectral width to fold back into the fold back into its spectral width. And what happens because of this? Because of this, there is a misrepresentation of the frequency from the regions outside the spectral width. Okay. So there will be misrepresentation of the data. So gets into the omega dash from the, and likewise the omega dash of the central spectrum appears in the, appears in the f omega of the next one. So what happens is that this frequency from the left, this moves into the central this, so as it is represented here, this is n equal to 0, n equal to +1, n equal to -1. So a signal from n equal to +1 moves into the signal from n moves to the spectral width of n equal to 0, and in a similar manner the signal which is present in n equal to 0, that's get folded back into into its next spectral width, n equal to -1 spectral width. Okay, so the central section got a frequency at omega s plus delta omega, right? So for example, this was omega s and minus omega plus delta omega. It got this was the frequency, but it got an extra frequency because of folding back of the signal, folding back of the signal from the neighboring spectral width. Okay, thus it appears as though omega dash is reflected around omega s frequency represented by the selected dwell time. So you can what it is trying to say that, so basically this omega dash is getting reflected around this omega s, and because of this omega dash which was present in n equal to +1, this got shifted to the n equal to 0, and this again is acting as a this again is getting reflected around omega s into this neighboring right side neighboring spectral bit. Okay. So that is the folding of signal. So folding of signals, this question was asked in week 3. The folding of signals in NMR spectrum occurs because of smaller spectral width than required, wrong pulse width, dwell time is smaller than the Nyquist equation, or wrong choice of pulse phase. So you can answer this question now that we have discussed the concept. So if the spectral width is not properly selected, then it causes folding of signals, and frequency from the neighboring spectral bit gets folded into the R region of interest, resulting in misrepresentation. Okay. So the answer of this question will be the smaller spectral bit than required. So if the spectral bit is smaller, and if it has a neighboring frequency, that will also come in the in our desired spectral bit that we have selected. Okay. Yeah. So this is what it is showing. So this is a figure. It shows that, for example, here we have taken a very large spectral width. So it can be, so both of these can cause folding of signals. Okay. I hope this concept was clear. Okay, now we will talk about analog to digital converter in Fourier transform NMR. So what is analog to digital converter? So what is happening in an NMR spectrometer is that all the data is getting recorded in analog form, but for storing it in the computer or in the system, that has to be converted into digital form, right? Digital form is in 0 and 1 form. So the data is getting continuously recorded in a continuous manner, but for conversion of but we are for storing the data, we have to convert the analog form into a digital form. So what happens in in Fourier transform NMR, the signal detected from the NMR experiment is an analog signal, right, which is continuous in time and amplitude. This analog signal needs to be converted into digital signal for further processing and analysis. And why is this concept necessary? Because this analog to digital conversion tells us about the resolution. It tells about the resolution of that will decide the number of signals, or the amount of data that can be stored. And the resolution of an ADC is the number of bits it uses to represent the analog signal. Okay, so number of bits means whether it is 4-bit or 8-bit or 16-bit. So that will decide what will be the resolution. The dynamic range of an analog to digital converter in FT-NMR refers to the ratio between the largest and smallest signal intensities that the ADC can accurately represent it. So what is the largest intensity and what is the smallest signal intensity that is present in our spectra, that will that is given by the dynamic range of an analog to digital converter. So it is a crucial factor because NMR signals can vary greatly in intensity, and the ADC must be able to capture both strong and weak signals within the same experiment. Okay, so ADC must be able to capture both the strong and weak signals. So what is the dynamic range of the ADC? That will decide the dynamic range of the ADC will decide what will be the resolution and what whether the large whether the small intensity and whether the strong intensities or the strong signal and weak signals both can be recorded or not. So a large dynamic range is essential in NMR because it allows the detection of low intensity signals without being overshadowed by high intensity signals. Okay, the number of bits used by the ADC determines the number of discrete levels it can represent. Okay, so for example, we have 2 bits, right? For example, we have 2 bits, and so 1 bit means it can be either in 0 or 1. So 2 bit means it will be 2 to the power 2. Okay, 2 to the power 2. So what are the combinations? It can data can be recorded or it can be stored. It can be 0 0. It can be 0 1 1 0 1 1. So that is why. So if there are n bits, then ADC with n bits can be represented in 2 to the power n levels. However, for signal representation, considering 1 bit for sign. So 1 bit is required for sign conversion. So the number of bits that are required for representing an ADC is given by 2 to the power n minus 1. Okay, so that is equal to 2 to the power n minus 1 minus 1. Why? Because one bit is required for conversion of sign. So this was also discussed. So based on this concept, one question is asked in week 4 assignment. So let's discuss a few questions to get this concept understand the concept better. So yeah, so consider an Fourier transform NMR with two signals of intensity ratio 2040 is to 1. What is the minimum ADC bit required to represent both signals? Okay, so here the ratio of the strongest signal and this is the weakest signal. So this is the strongest and weakest signal that needs to be recorded is given. So, the maximum strongest signal that you need to record is 2048, and the weakest signal that needs to be recorded is 1. So, based on this information, you have to tell that how many bits will be required so that both the weakest and the strongest signal can be represented. Okay. So try this question. So basically, the dynamic range of the FT-NMR is given. So how many bits would be required to store both the to store the range to store a range of intensity starting from 1 to 2048. Dynamic range is given by 2048 by 1. So one bit is all it will be required for one bit will be required for sign conversion, right? Yeah. So for sign conversion, one bit is required. So leaving that number of bits that will be required will be 2 to the power n. So 2 to the power n bits can be used for recording this range of signals. Okay, leave this one bit. So leaving this one bit because the here this is getting utilized not for storing the signal. So you can consider 2 to the power n number of bits. So 2 to the power n is 2048. So now you can calculate n. So what will be n? N will be 11. Okay, n will be 11. So the dynamic range of the Fourier transform NMR is 2048 and the number of bits required to cover the dynamic range excluding the sign change. Excluding the sign change is if we exclude this one bit, then the number of bits that will be required will be 2 to the power n. And so since 2 to the power n is equal to 2048, so n must be what? N must be 11, right? N must be 11. N must be 11. N must be 11, and so now adding another bit, so the minimum number of bits that will be required will be 12. Okay. So the answer will be 12. These will be the minimum number of bits that would be required. So remember the formula 2 to the power n plus 1, and based on this formula a few questions have been asked in week 4 assignment also. You can try out the question. You will get using this one, you can get the answer. Now, there is another question based on this, that if you have a sample with three signals of intensities 8,000, 8,502 in arbitrary units, if the ADC has a 14-bit resolution, determine whether all the three signals can be accurately recorded. So, three different signals have been stated in this question, 8,502. So 2 is the minimum intensity. Weakest signal will have 2 intensity and the highest signal will have this intensity 8,000. So here also this dynamic range is given. So starting from 2 to 8,000 and for representing this dynamic range, where you have been asked whether this 14-bit resolution is sufficient or not. So try out this question and then we will discuss it in 2-3 minutes. So 14-bit resolution means one bit you can exclude the one, you can exclude one bit because one bit will be used for the sign conversion. And now you can consider 13 bits. And so there are 13 bits and whether these signals can be accurately recorded. So you can calculate 2 to the power, what will be 2 to the power 13, and you can get the maximum intensity that can be recorded. And depending on that, what is the maximum intensity, you can tell whether these intensities can be recorded using this number of bits. Okay. So how much is 2 to the power 13? You use a calculator. You can tell me. So yeah, so 2 to the power 13. So let's look at the solution to this question. So 2 to the power 13 is 8192. Okay. And the dynamic range for this ADC is, what will be the dynamic range? The dynamic range is just now we discussed that dynamic range is the maximum intensity divided by the minimum intensity. Okay, so the maximum intensity given in the question is 8000 and minimum intensity is 2. So that is 4000. 4000 is the dynamic range. So, so therefore, all these signals can be accurately recorded, right? Okay, is this question clear? So, these all these three intensities represented, can be represented or can be recorded using a 14-bit resolution. Because 2 into 4, if you do 2 into 4000, you will get 8000, right? 8000. Therefore, this 8000 intensity can also be recorded. And also, we found that the maximum intensity that can be recorded is 8192. And so 8000 is below 8192. Okay, 8192. So this maximum intensity can also be this 8000. This is a maximum intensity. This can also be recorded. And the minimum intensity, this this comes in the dynamic range. And so all these intensities can be accurately recorded. Okay. That was the concept of EDC. You can try more questions. They are in your assignment. Now moving to the next question. In NMR, the loss of small signal of sample due to large signal of solvent is due to. So what we had discussed here also, that the ADC must be able to capture both the strong and weak signals within the same experiment. So if the dynamic range is not large, then what will happen is that the signals which are having weak intensity, that will get shadowed, or they will be suppressed by the signals which are having high intensities. Okay, so you have to decide on what should be the ADC, because the ADC control the ADC, or what is the number of bits control the will control what will be the dynamic range of the FTNMR. So, so in this question, that what is they are saying, that there is loss of small signal of sample, small the signals which are having weak intensities, that are getting lost due to large intensity of the solvent, because whenever there is a sample in whenever there is a sample, the sample whatever sample we have, it can be protein sample or it can be any other biomolecule. Protein, there will be the solvent. The sample will be present in a solvent, in a buffer, or in there will be a solvent. So if the signal that is produced by solvent is very high, then it can cause suppression of the signal of our sample, right? So for to avoid that, what we have to do, that our dynamic range must be high, right? Must be high, but usually what is preferred, that beyond 15 bits, the dynamic range is not kept. Usually the dynamic range is kept below 15 bits. Okay, below 15 bits. So there is loss of small signal of sample because of dynamic range problem. Okay, that is the answer. Option B. Yeah, so just now what I was discussing, discussing about solvent suppression. So because our sample is present in a solvent, so what happens is the solvent can suppress the signal of the solvent can suppress the signal of our desired macromolecule, So in many NMR experiments, especially in solution NMR, does a solvent is used, and that solvent, yeah, because it is present in much higher concentration than the solute, it results in strong solvent peaks. It results in strong solvent peaks that can overwhelm the weaker signals from the solute, making it difficult to analyze the compound of interest. Okay. So there was a in the slides you can find there are two spectra, one where the solvent peak was not suppressed and another in which the solvent peak was suppressed. So in presence, if we do not suppress the signal that is coming from the solvent, then we will not be able to observe the weaker signal that is coming from our sample. Okay, that is coming from our sample. So now there are several methods that were discussed in the lecture, how we can suppress the solvent. Now, let's discuss this particular method of solvent suppression, which is known as the jump and return pulse sequence. Because based on this, you will find a few questions, and for a greater other understanding of the other methods of solvent suppression, you can go back to the videos and watch them. So let's discuss this concept, because that will help you in solving the assignment. So what happens in jump and return pulse sequence? This is another method of solvent suppression. And here in jump and return pulse sequence, what happens is first a short low power 90-degree RF pulse is applied. First, we apply a short low power 90-degree RF pulse. 90-degree RF pulse means a signal is applied which will uh, cause the magnetization to flip by 90 degree, and this pulse jumps the magnetization of the solvent from its equilibrium position into the transverse plane. Okay, the transverse plane is the xy plane and the equilibrium position is the z axis, right? Is the z axis. So in this z axis, this is the z axis, consider this is the y axis and x axis, and this is the y axis. Okay. So you apply an RF pulse, and depending on which direction you apply the RF pulse, it will cause the bulk magnetization to flip from its equilibrium position, which is along the z-axis, to the either it can move in the positive x direction or it can move to the y direction. Also, it will shift somewhere in the xy plane. Okay. So after this initial pulse, a short delay is introduced. During this period, the magnetization of the solvent dephases due to inhomogeneities in the magnetic field and interaction with other solvent molecules. Okay. So once you remove the RF pulse, this the magnetization of this solvent molecules, they will dephase out from the transverse plane, and they will start moving to the longitudinal plane, towards the x-axis, z-axis, towards the z-axis. And then after the so in this short delay, because the solvent molecules are in a have a higher are present in higher amounts than the sample, they will start dephasing out. And after that, after this short delay, so what we are doing is we are applying a 90-degree pulse. We are giving a short delay for tau. For example, consider a tau delay is applied, and then again we are applying a second 90-degree pulse. So once the second 90-degree pulse is applied, what will happen? So let's consider an example. So for example, the our RF pulse is applied along the positive y-axis. Okay, consider that the RF pulse is applied along the positive y-axis, and this will cause the magnetization to shift from the z-axis to the x-axis. Z-axis to the x-axis. Now there is a short delay. In this short delay, due to magnetic field inhomogeneities, the solvent molecule will dephase out. Solvent molecule will dephase out, and after this short delay, again a 90-degree pulse is applied. So if a 90-degree pulse is applied again, then what will happen? Now um, the magnetization of the sample of the nuclear spins that were it had directed in the x-axis, they will again, because of this 90-degree pulse, they will move to the y-axis, right? They will move to the y-axis. Now in this y-axis, we have the receiver, and But the solvent molecules, what happens is that the solvent molecules have dephased out, but this so the sample, the nuclear spins of the sample, they will shift, or that will cause another 90-degree pulse will cause the shift from the x-axis to the y-axis, and this pulse returns the magnetization back towards the pulse returns the magnetization back to the, because the magnetization has dephased during the evolution period, the return pulse does not perfectly realign the magnetization along the z-axis, leading to partial cancellation of the solvent signal. So let us look at this figure. So what happens is this jump and return pulse sequence. So this is the figure. So first we have applied a 90-degree pulse along the x-axis, and then we have given a short time delay for tau seconds. And then again, we have applied a 90-degree pulse along the negative x-axis, and then we are recording the signal. So look at this figure. So first, both this, so this in the blue arrow, this blue arrow shows the magnetization. So shows the magnetization of the solvent. Okay, solvent magnetization. And this orange colored arrow, this shows the magnetization of the sample. So the nuclear spins of the sample that will have a bulk magnetization. So both along the z-axis. So both the solvent magnetization and the magnetization of the sample, both will be directed along the z-axis. Now what happens? Now on along the x-axis, an RF pulse is applied. 90-degree RF pulse is applied, and since 90-degree RF pulse is applied, this will shift to the negative y-axis, and then another delay of tau second is applied. Now in this tau second, what will happen? uh, in this tau second in this tau second, so as you can see that this solvent molecules have a different magnetization. They will have a different frequency of rotation, and frequency of precision, and they will start dephasing out from the xy plane, and they will start dephasing out from the xy plane. Now when again this minus x pulse 90-degree pulse in minus x axis is given, this signal, this the signal of the solvent molecules, it remains, but this one. Okay, so what happens? The solvent molecules, since they are directed in the minus y-axis, minus x-axis, this will cause this solvent molecules to return back to their equilibrium position. But the solvent molecules, the magnetization of the solvent molecule remains in the x-axis, and hence we get the signal of the only the solvent molecules. And in this way, the magnetization, the signal of the solvent molecules is suppressed, but we can get the signal of our sample. We can get the signal of our sample. Okay. So if the excitation, so remember this one. So if the excitation has to be, so what is the pulse sequence in a jump and return jump and return solvent suppression method? So it is 90-degree X, then a delay of tau, and then another 90-degree in the minus X direction. Okay. So minus when this 90-degree x 90-degree pulse along the minus x direction is applied, it causes the solvent molecules to move back to their equilibrium position along the z-axis, so that we do not record any signal in the do not record signals of the solvent molecules, but we can record signals of the solute molecules, which are directed, which will remain in this x-axis. Okay. Okay. So if the excitation is to be maximized at a frequency nu max away from the offset, then tau is set equal to 1 by 4 nu max. So this what should be the value of this delay time, or what should be the value of this tau? So usually what is done, this tau, the value of this tau is set to 1 by 4 nu max. Okay, is set to a value nu max. And what is nu max? Nu max is the, so is the maximum frequency. So for example, you have a sample. You have a sample which is present in a solvent. So this sample, it will have a particular frequency, for example, for 10 ppm, and there will be solvent molecules. The solvent molecules, because they are present in very high concentration, they will have a larger intensity, and they will have, for example, they are present in 4 ppm. So this is called the offset frequency. Okay. So this is called the offset frequency away from the new. So that should be this difference. For example, this is 5.3 ppm, right? So that should be, so that tau should be 1 by 4 times of the nu max. Okay. So this is the offset. So you can easily convert this ppm into hertz value. We had already seen how we convert ppm into hertz, and so the depend. So that should be the value of tau, if you want to, for suppressing the solvent signal using this jump and return method. Okay. I hope these points are clear. Hmm. Okay. So, so yeah, this is what I was explaining, that what is offset. The offset frequency is the frequency of that the frequency that is what I can say is, so this is the desired frequency. The desired frequency is the frequency of the sample. We want to record the frequency of the sample. But other than this frequency of the sample, the frequency which is present in the solvent, it can be water or any DMSO or anything. That is the offset frequency. So so here what he has, this question they have asked is that, so yeah, this is the offset. Hmm. Yeah, so that is what it was saying in this question, that if the excitation is to be maximized at a frequency nu max away from the offset, then the tau is set equal to 1 by 4 nu max. Okay, so in this question, in jump return sequence for water suppression to excite a spectral region of 2000 hertz away from water. So you want to excite a spectral region which is 2000 hertz away from water. What should be the value of tau in millisecond? So here, yeah, I have shown this figure to so that you can understand what is meant by offset. And so this is just this figure does is has nothing to do with the question, but this is just for your understanding that what this question is trying to say. Here, this 5.3 ppm does not correspond to 2000 hertz. This is just for representation. I have given this figure. I've shown this figure. So it says that this is, for example, this is the spectral region. So this is the spectral region that you want to excite, and this is the spectral region you want to excite, and this spectral region is 2000 hertz away from the offset. So what should you keep the value of tau that you have been asked? So just now in the previous slide, we saw that the value of tau should be 1 by 4 times nu max. Okay, 1 by 4 times nu max. So now using this formula, you can get the value of tau. You can put the value of nu equal to 2000 hertz. Put the value of nu equal to 2000 hertz. So remember that nu is the frequency that is away from the offset frequency. Away from the offset frequency, what is the frequency? That is 2000 hertz. So now if you calculate this, you calculate the value of tau, then 1 by 4 into 2000, what you will get is 1 by 8000. And how much will you get if you do 1 by 8000? So you have been asked that you have to find the value of tau in millisecond. Okay, so it will be 0.125 into 10 to the power minus 3. So 0.125 into 10 to the power minus 3 means 0.125 milliseconds. Okay. So the answer of this question is 0.125 milliseconds. So you will find these type of questions in assignment 4. You can, yeah. So after you go through this video, you can try and solve this type of you can solve these questions which are there. Yeah. So we'll look at the solution once again. So just a second. So here the spectral frequency, the frequency that you want to excite is 2000 hertz away from the offset frequency. Okay. And so you can get the value of tau by just by using, yeah, that is, it is given by 1 by 4 times nu max. And so 1 by 4 into 2000, 1 by 8000, you will get 0.125 milliseconds. Okay. Now, next we will discuss the concept of spin echo. So spin echo is another method which is used in FT-NMR. So in FT-NMR, what we were seeing is that we are applying an RF pulse, and then after the RF pulse is removed, the magnetization starts to dephase out from the transverse plane, right? It starts to dephase out from the transverse plane and moves to the z-axis. So these are different cases of different modifications. You can say there are modifications of one pulse FT-NMR. One pulse FT-NMR means we are only applying a single pulse. We are giving a single RF frequency pulse, and this RF frequency pulse, it can be 90-degree pulse, 180-degree pulse, and then after that we are recording once this RF pulse is removed. We are recording the FID basically. We are recording the free induction decay. We are recording the free induction decay, and because of the from this Fourier induction decay, we can get different informations about this T1 relaxation, T2 relaxation. So what are the T1 and T2 relaxation? So we discussed that T1 is the transverse. We discussed about transverse relaxation and the longitudinal relaxation. So longitudinal relaxation would mean that the bulk magnetization, which are there is loss of coherence in the XY plane, and then there will the longitudinal relaxation means the magnetization which had oriented in the X direction, it will now again move back to the Z direction. So that is longitudinal relaxation. So there will be exponential rise of signal, and transverse relaxation means the signal will there will be decay of signal. There will be decay of signal. Then the signal which was in the X direction, it will start decaying, and that is given by the transverse relaxation. That is given by the transverse relaxation. Okay. So in spin echo, what is the pulse sequence that is given in spin echo? In spin echo, first a 90-degree 90-degree RF pulse. A 90-degree RF pulse is applied along the x direction. Okay, 90-degree RF pulse is applied along the x direction. Then a delay of tau seconds is given. Then again 180-degree. Again, a 180-degree pulse sequence is given in the x direction. And after that, there is a delay of tau. And after that, we record the frequency. Okay, so let's understand this with the help of a diagram in the which is shown in the next slide. So what happens? So first, so remember the sequence. The sequence is 90-degree followed by tau, 180x, and then we record the echo. Echo is the we will record the signal after this point after 2 tau. So what happens? The first 90-degree pulse, 90-degree pulse tips the next net magnetization into the transverse plane. So first our magnetization was in the longitudinal plane, and when a 90-degree pulse is given after the application of a 90-degree pulse, so consider this figure. In this figure, a 90-degree pulse is applied along the x-axis, and this 90-degree pulse along the x-axis, it causes the magnetization to flip from the z-axis to the minus y-axis. Then after that, there is a delay of tau seconds. Delay of tau seconds. Now in this t second delay, what will happen? In this t second delay, so these here A and B, these are not the solvent and the sample, but this blue and orange colored lines, these represent different nuclei. For example, here they have shown that this blue color is representing A nuclei and B color, this is representing the arrow is representing the B nuclei. Okay. Now in this tau second time delay, the RF pulse is removed, and these nuclei will have their own precision frequency, and they will start decaying. They will start once this frequency is removed, they will start to rotate in their own frequency, and they will start moving from the XY plane. Now, then after this tau second delay, again the spins, yeah. So over time, the spins will begin to dephase. And then after this t second delay, a 180-degree pulse is applied. So after now a 180-degree pulse will be applied along the x-axis. And this 180, what will happen if you give a 180-degree pulse? Now these will shift. They will completely flip about the x-axis. About the x-axis, this A and B nuclear spins, they will completely flip, and they will remain in the same plane. All right. They will remain in the XY plane because you have applied a 180-degree pulse. You have not applied 90-degree, you have applied a 180-degree pulse. So they will completely flip about the x-axis, and their rotation will change. Okay. So they were, yeah. So so now what happens is that this pulse inverts the spin. So first this, for example, you can consider that one nuclear spin was precessing faster than the other. But after this 180-degree pulse, the slower, the nuclei which was precessing at a lower speed, that will catch up the one which was moving at a faster frequency. So there will be rephasing. So first in this, what happens? First we are dephasing. In spin echo, what we do is first we are dephasing the nuclear spins, and then we are rephasing it. So when we are applying the 90-degree pulse along the x-axis, there is dephasing of signal, and then when 180-degree pulse is applied along x-axis, there will be rephasing of the signal, and this rephasing is called spin echo. So after the 180-degree pulse, the spin continues to precess, but now the faster spins, those that had dephased more, so the faster spins will have a higher will show more dephasing, and they will catch up with the lower spin. So at time t2, the t tau, the spins rephase. So after this 180-degree pulse is applied, we wait for another tau second, and in this tau second, what happens? The faster spins will catch up with the spins that were having a lower frequency, and the spins will rephase. Okay, now both this will be rephased, means they will be along the aligned with each other, and this results in the formation of a spin echo, a revival of the net transverse magnetization. So initially we had seen that this was the that both were in phase. Initially, what happened? Initially, both were in phase. Now, finally, after this pulse sequence, 90 tau, 180 tau, and after this delay, both these again come back to their they again come in phase, and this will give us the net transverse magnetization. Okay, so I hope that is clear. Hmm. So this is the concept of spin echo. So remember that the pulse sequence that is used is 90x tau, 180x tau, and then so after both the nuclear spins or get rephased, we record the signal. Okay. So now what happens if in case of a weakly coupled AX spin system? What will happen in a weakly coupled AX spin system? So yeah, so we had to discuss the concept of a weakly coupled system, strongly coupled system. So A and X are weakly coupled spin system. So in case of weakly coupled spin system, after the first 90-degree pulse, the magnetization vectors corresponding to the transitions A1 and A2 of spin A are along the negative y-axis. That so it is similar to what we had seen for the non-coupled spin system. So similar to this, when this 90-degree pulse is applied, both this the magnetization will flip to the negative y-axis. Now during the next tau period, they precess with different frequencies in the transverse plane and dephase. Okay, so now these are different nuclei. So these different nuclei will they will precess with different frequencies. They will precess with different frequencies in the transverse plane, and they will dephase. Dephase means they will start shifting away from the xy plane and moving to the longitudinal plane. And now the angle. So remember this, that the angle between these two vectors, this A1 vector and A2 vector. So A1 vector and A2 vector are the magnetization vectors corresponding to the A1 nuclear spin and A2 nucleus, or the A spin. A nuclear spin has a magnetization A1, and the A2 nuclear and the X spin X nuclei has an A2 magnetization. So what is the angle after this tau? After a delay of tau is applied, the angle theta between these two vectors is given by 2 pi j tau. So what is j? So we had discussed J is the coupling constant. J is the coupling constant between the two nuclear system, between the A nuclei and the X nuclei. So this um, so since these are different nuclei, they will have these are different nuclei. They will precess with different frequencies. And what is the phase difference between these two frequencies? It is given by theta equal to 2 pi j tau. Okay. Now again a 180-degree pulse is given. Again a 180-degree pulse is given, and and after so similar, so it is the same case. So we are applying a 90-degree pulse along the x-axis, then a delay of tau is given, then again a 180-degree pulse is given along the x-axis, and after a delay of tau we get the echo. We record the signal. Okay, so now during the next tau period, there will be another phase difference. So total there is two. So after So there is a delay of 2 tau. So that will result in a phase difference of 4 pi j tau. Okay, 4 pi j tau. During the next tau period, the two transitions continues to dephase further, and at the end of 2 tau, the angle between them will be 4 pi j tau. So what you can see in this weakly coupled AX spin system, so in contrast to what we have seen in the uncoupled spin system. In the uncoupled spin system, we saw that both the spins were aligning along the y direction. Okay, but after this 180-degree X pulse, and after this tau second time delay, these will not align, and there will be a phase between these two spin systems, which is given by 4 pi j tau. Okay. Now the important now another thing is that the echo amplitude in the spin echo experiment is proportional to e to the power minus 2 tau by t2, e to the power so the echo amplitude that we were recording after this tau delay. 180 degree, and tau, that is the spin amplitude. So this spin amplitude will be proportional to what? This is the amplitude. This spin amplitude will be proportional to e to the power minus 2 tau by t2. Okay, thus fitting the eco-amplitude to the data obtained for different values of tau allows the measurement of T2 relaxation time. So, so if we are so for different values of tau, so if we apply different, we will apply different values of tau, and then we can record what are the T2 relaxation time. What are the for different values of tau? What are the different T2 values? The precise refocusing of the signal in the spin echo experiment is dependent on each nucleus remaining in constant magnetic field during the time 2 tau. So the precise refocusing of the signal. So just we have seen that first there will be when the 90-degree pulse is given, there will be dephasing, and and after that 180 there will be refocusing of the signal is dependent on each nucleus remaining in constant magnetic field during the time 2 tau. If, however, there is molecular diffusion during this time between regions of different field strengths because of field inhomogeneities, then the echo amplitude will be modified and we do not get the true value of T2. So because of magnetic field inhomogeneity. Magnetic field inhomogeneity means that the magnetic field is not uniform throughout the system, and this can result in different T2 values. Okay, this can result in different T2 values, and hence this echo amplitude. Because this echo amplitude is dependent on the T2 value, this echo amplitude will get modified, and hence we will not get the true value of T2. So remember this, that the echo amplitude is proportional to T2. Okay, T2 is the transverse relaxation. Okay. So yeah. So let's attempt this question now. The spin echo pulse sequences. So just now we had seen what is the spin echo pulse sequence. So there are four options given in this question. 180 degree, tau 90 acquired, 90 tau, 180 tau acquired, 90 tau, 90 tau acquired, 90 tau, 180 tau by 2 acquired. So what we're doing in spin echo experiment. So first we were applying a 90-degree X pulse. Then we were giving a delay of tau second. In this tau second, the nuclear spin will start dephasing out. Okay, and then we were applying a 180-degree X pulse. And after this 180-degree X pulse, a delay of tau second is given. So in this tau second, there will be refocusing of the signal, and then we record the signal. We record the spin echo signal. Okay, spin echo signal. So now you can answer this question. So the correct answer to this question is option B, right? So 90 tau, 180 tau, and then acquire. So the spin echo refocuses all chemical shift, some chemical shift depending upon frequency, coupling evolution between two coupled spins does not refocus chemical shift. So spin echo, what will it do? So try out this question. So what is this question asking? So what gets refocused after when we record this spin echo when we record this experiment? So whether all the chemical shifts will be refocused, whether some chemical shift will be refocused depending upon frequency. So the spin echo refocuses all the chemical shifts. Okay, it will refocus. So once this 180-degree pulse is applied and then we wait for another tau second. After that, all the chemical shifts will get refocused. All the chemical shift gets refocused. So that is what I was discussing, that the 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 nuclear which were having a the precision frequency that were precessing faster, will catch up with the nuclear spin that were precessing slower. And so all the chemical shifts get refocused after this 180-degree pulse and after this delay of tau second. So this tau second is set to such a value so that all the chemical shifts gets refocused. And after the chemical shift gets refocused, we record the signal. Okay. The answer is option A. Now there are two more questions. So in a spin echo experiment on a coupled two spin AX with coupling constant two spin system. So there is a two spin system AX and the coupling constant between these two system is J. Between these two systems is J. The phase difference between the two components of the doublet at the time of echo will be. So what will be the phase difference between the two components of the doublet at the time of echo? So I discussed this question. This is one of the questions that is asked in your assignment 4. So after this 90-degree X pulse, we wait for tau. There is a delay of tau second, and in this tau second, the two nuclear spin will start dephasing out. And since this is a case of weakly coupled system, AX is a case of weakly coupled system. The phase difference between these two systems, theta, that will be given by 2 pi j tau. Now after a delay of one so delay of tau second, the theta will be 2 pi j tau. Okay, but after that we are again applying a 180-degree pulse and then we are giving a delay of tau second, another tau second. We are giving a delay of another tau second. So in this case, the phase difference between the two component system will be what? It will be 2 pi j into 2 tau because we are giving a delay of 2 tau. So that will be equal to 4 pi j tau. Okay, 4 pi j tau. So at the time of recording at the time of echo spin, yeah. So at the time of spin echo, what will happen that because of 2 tau delay, the phase difference between the A nuclei and the X nuclei will be equal to 4 pi j tau. Okay. So the correct answer is 4 pi j tau. You can also try this question number 12. The echo amplitude in a spin echo experiment decreases due to. So we had we just now discussed that the echo amplitude. The echo amplitude is given by e to the power minus tau by t2. Is given by e to the power minus tau by t2. Okay, and the echo amplitude decreases. Why does this echo amplitude decreases? So what we found that in a spin echo experiment, first we are giving a 90-degree X pulse, then tau, then a 180-degree X pulse, then tau, and then we are recording the echo. So why is there a decrease? The echo amplitude. So as we see that the echo amplitude, so we see that with time the amplitude gets decreased. So why is this happening? So we just now discussed that because of inhomogeneous in an in a because of translational diffusion in inhomogeneous field. So in a homogeneous field, what will happen? There will be diffusion of this the two nuclear spins, and hence with time, what will happen? The echo amplitude will be decreasing. Okay. So this was based on this concept. So if there is a molecular diffusion during this time between the regions of different field strength. So this is the sample. This is our sample. And because the because of the magnetic field is not homogeneous, if the magnetic field is not homogeneous, and because of the difference in magnetic field in different regions, there will be this will affect the T2. This will affect the T2 value, and hence the eco amplitude will start decreasing with time. Okay. So if there is molecular diffusion during the time T2 between regions of different field strength, because of inhomogeneities, if the magnetic field is not constant, the echo amplitude will be modified and we do not get the true value of T2. Okay. So we do not get the true value of T2, and hence we also there is also a decay in the echo amplitude. The echo amplitude also decreases because of this reason only. Okay. So I hope so. This is all for this. Yeah, one more concept. Uh, One more concept that requires a little bit more discussion, so that this based on this concept a few questions are asked. So this concept is signal averaging and pulse repetition. So what happens in signal averaging? In signal averaging, the signal averaging between two successive scans should be optimized. So what happens is that uh, so this RF pulse is applied. So there is a pulse sequence, right? So there is a pulse sequence. So, for example, just now we had seen the pulse sequence for the eco spin experiment. So the different experiments have different pulse sequence, and what the scan means we are giving this pulse sequence at different intervals of time. So in scan one we are giving that one pulse sequence. Then again, this scan one is for a particular time. Then again we are repeating the scan and giving it in intervals. So in signal averaging, the what is the average this time should be optimized. So what is TP? So you can see in this figure the time TP is the time interval of one scan. So time interval of one scan means, for example, as we had seen in spin echo, that we are giving a 90-degree X pulse, then a delay of tau, then 180-degree X pulse, and then another tau. So that the entire time that is required for this pulse sequence is considered is given by TP. So TP is the time for one pulse sequence. Pulse sequence, what is the time that is given by TP? Now the TP must be longer. So why the TP must be longer? The TP must be longer so that the magnetization can relax back to equilibrium before the next scan. Okay. The magnetization which had after the pulse which had oriented in the XY plane, that needs to relax back to equilibrium, and so this TP should be longer. But however, what happens is that if we give a very long delay time, then what will happen? Then this can also introduce noise in the signal. So because of introduction of noise, it decreases the signal to noise ratio. So if it has a very high, if it is a very high TP value, if the TP value is very high, then what will happen? That the signal to noise ratio will also decrease. So so because of these issues, the this TP value should be optimized. And how can we optimize this TP value? So TP value is dependent on two factors. One is the relaxation time and another is the flip angle. In relaxation time also it is dependent on T1. So the flip angle is given by cos beta optimal equal to E1. So beta optimal is the angle. It is the optimal angle. It is the optimal angle for that can be set for this for setting this TP value. And this is given by cos beta optimal equal to E1, where what is E1? E1 is E to the power minus TP by T1. Okay, so different nuclei will have different relaxation time, and this relaxation time will, based on the relaxation time, we can accordingly optimize this T1 value, and we can optimize the TP value to get what will be the optimal flip angle, and this flip angle will give us the TP value. Okay, so what should be the TP value? So now one thing that you should consider here, that for carbon 13, so for spins which have very long relaxation times, where the T1 value is very high, where the T1 value is very high, the usually small flip angles are favored and faster repetitions are generally favored. Okay, so if the T1 value is very high, then what will happen? Then this can introduce noise in the signal, and so to avoid this, the what we do is, because the T1 is very high, we keep the flip angle small. The flip angle is kept small. Okay, so that flip angle is kept small so that noise is not introduced in the signal, and this two can be these two signals can balance each other. Okay. So if the T1 is high, we keep the flip angle low, and if the T1 is low, we keep the flip angle high. So in this way, we can adjust the value of TP. So TP is the time for one. What is the time required for one scan? Okay. So remember this concept. This is an important concept. This concept will help you to solve few questions that are asked, and so this was all for today. Uh, I hope these concepts were clear. So if you have any doubts, you can ask me, or we can discuss all these concepts in more detail in the next lecture. And if you have any more doubts, we can also take up those doubts. So usually what is done is this theta is usually taken to be 30 degree uh, for nuclei which have large relaxation times. So so that was all for today. I hope this session will be useful for solving your assignment. So yeah, thank you all for your patient listening, and we will end today's session here. Thank you.